In this work, we will introduce an antistatic gradient estimator for binary latent variables, which we call it DisARM. This is the work done at Google Research and DeepMind, jointly by myself, Z, and Andre and George. The work has been accepted at NeurIP's 2020 Spotlight paper. We consider the problem of optimizing the following training objectives with respect to the parameter zeta of a factorial Bernoulli distribution QB, where B is a binary latent variable. The description covers many problems with discrete latent variables. For example, in variational inference, FB is instantaneous elbow and QB is a variational posterior distribution. And in conditional computation, discrete variables can specify which part of the large model should be evaluated. The gradient with respect to zeta can be expressed as the following term. The second term can typically be estimated with a single Monte Carlo sample, where the Monte Carlo estimates for the first term can have large variance. So low variance unbiased estimator of the first term will be our focus. Previous work on gradient estimator of discrete random variables of two types, defined by whether or not using continuous relaxation. The first type, using the continuous relaxation, is appealing because they result in low variance estimators by taking advantage of the gradient information. But they are not always applicable. For example, in conditional computation, using the relaxation would require evaluating the entire model every single time of evaluation. The computational cost could be prohibitive. The example of such a kind of method includes Gumbel softmax, concrete, rebar, and relax. The second one, without using continuous relaxation, has historically been an estimator of choice for the models with discrete random variables due to their unbiasedness and fewer requirements. But they usually exhibit high variance, and previous work has been focusing on augmenting them with variance reduction methods to improve their practicalities. The examples of those methods including NView, WMCO, and ARM, where ARM is a method we build upon. So ARM stands for Augment, Reinforce, Merge. The key idea is to use antistatically coupled pairs of samples to derive the gradient estimator, instead of using the independent samples. So the intuition behind it is that pairs of antistatically sampled, by definition, are pairs of negatively correlated samples, which can cover the sampling space better than independent samples. However, Bernoulli random variables cannot be directly antistatically sampled, but it can be reparameterized in terms of logistics distribution, for which we can introduce antistatic pairs, as shown in the equation, which is the epsilon and negative epsilon, which are logistic samples and antistatic samples. ARM only evaluates F at discrete value, so does not require continuous relaxation. We expect that such an estimator would have lower variance because the learning signal is the difference of evaluation of F. ARM reduces the variance where antistatically coupled, but it also increases the variance due to the reparameterization. It is not clear that this translates to the overall reduction in variance. So in DisARM, we introduce another level of trick to further reduce variance. DisARM integrates out the continuous randomness in ARM and only retains the discrete component. So estimator only needs to evaluate at discrete values. As shown in the formula, we integrate out Z conditioned on B and B tilde, result in a gradient estimator guaranteed to have lower variance than ARM. So here we show one example in the paper, and we compare the performance of ARM, the green curve, DisARM, the red curve, relax, the blue curve, which is the SOTA method with continuous relaxation, and the two independent sample reinforced estimator with a lead one out baseline, which is we call it reinforced LOO, which is orange curve. And we evaluate the three measures on networks with both linear and nonlinear activations. The left column is the training objective elbow. The mid column is 100 sample bonds on test set, which is a proxy for log likelihood. And right column is the variance of the gradients in log scale. And DisARM is reduce the variance over all method without continuous relaxations. And with continuous relaxations, relax performs better in linear network, but this doesn't hold for nonlinear networks. Furthermore, training DisARM, ARM, and reinforced leave-one-out is twice as fast as relax on a P100 GPU. Please find more detail in our papers, and the code is also available online. So the paper will be presented at NeurIPS 2020 as a spotlight paper. There are covered more details. Thanks a lot.